Welcome. In this video I'm going to show you how you can analyze a single nominal variable using Python with my stikpetP library. I'm using JupyterLab with a Jupyter notebook and a Python 3 kernel. So in this video I'm going to go over the steps to create a frequency table, make a bar chart, determine the mode and the variation ratio, then perform a Pearson chi-square goodness of fit test, the Kramer's V for goodness of fit as an effect size measure for that, then perform a pairwise binomial test, and last to a CoNG as an effect size measure for that pairwise binomial test. So we actually can simply use one of the functions in the stikpetP library for that. There are also some alternatives for each, as you can see here. They're also in this Jupyter notebook. I'll quickly go over them, but I'll leave a link to this Jupyter notebook in the description below. So first off, to install my library, I don't have it on PyPy, so you will need to install it straight from my GitHub. So you can run pip install and then just use my stikpetP GitHub account. I also have a no cache version in case I recently updated something, but one of these two should work just fine. After that, we can actually import it, and that's the first thing I'll do because I already installed it. And of course, I'll need an example. So I'm going to be using a CSV file, so I'm going to be using pandas to load that in. So import pandas, and then use pandas read CSV to simply load that CSV file in. It has a comma as a separator, so that might be useful. And I only need one of the fields, so let's use the marital status, which was a nominal field, and the first 5 are now shown. To get a quick impression of the data, we can now use the frequency function tab for table frequency of that data, and here we get to see the frequencies, the percentages, the valid percentages, and the cumulative percentages. As you might notice, percent and valid percent are not the same because percent includes missing values that are not shown here, so these won't add up to 100%, and the difference will be the ones that didn't answer any of the questions, or at least not this question. To visualize the results, we can use a simple bar chart, and I'll put in as percentages. So now we nicely have the bar chart, the visualization of the table. The same outcome, the married was chosen quite often, then the never married, and separated the least. Now there are some alternatives, you can see those in the appendix. It's not quite often reported, or at least I don't see it that often, but the one that is the highest bar, the one that was chosen most often, is known as the mode, which is the only measure of central tendency that we can actually use for a nominal variable, and this simply shows then the mode and the highest frequency of that mode. The nice thing about this function is that if there are 2 or more with the mode, it will actually show and list all of them. Then we can have the variation ratio as a measure of spread or dispersion. There are quite a lot of these actually, so in the alternatives you will see a one function that has a lot of different measures for this, but it's kind of an indication of how much variation there was between the frequencies. Now to test if one of the groups or categories was selected significantly more often than at least one of the others, we can run a Pearson chi-square test of goodness of fit. So simply use the Pearson GOF, TS for test, and then Pearson goodness of fit test. It will give you all the output you will need for the reporting. The most important ones are that this one should be at least 5, the minimum expected count. Some say it should even be a minimum of 1, depending on whose thresholds you want to use for this. The p-value is below 0.05, so that means that there are significant differences. We can use the Kramer's V for the goodness of fit tests as an effect size measure. This requires the n and the number of categories, which of course is nicely in our test results. So I can just obtain those and then use the ES Kramer's V goodness of fit test, enter the chi-square value, which is the statistic, the n and the k, and we get ourselves Kramer's V. In this case 0.4011 something. We can convert this to a Cohen's W using the ES-convert function. So then Kramer's V for goodness of fit, convert it to Cohen W, and it needs also then to know how many categories there were, so that was K in this case, and we can fill that in for the extra variable parameter 1 here, and use of course ES-convert from effect size convert, and this is then Cohen's W. We can then use rule of thumb for Cohen W, which is available by using TH for thumb rules, and then Cohen W. Enter that W value we found, and in this case it can be considered large. Now all of this only shows that there are differences, significant differences. We then of course would like to know which ones are different, so we can perform a pairwise binomial test. We need to adjust for that, so in this function it will actually use a Bonferroni correction, and then it will do all pairwise comparisons for you. So that's quite a lot of output, but it simply compares married versus never married, married versus divorced, etc. It shows how many were in each of those two categories, the observed proportion of the first category, so 71% is married if you compare it to category, never married, sorry. The expected proportion 0.5, you would expect a 50-50, and the p-value, and then the adjusted p-value for that. All of these seem to be still far below the 0.05 threshold, the usual threshold, so they would all be significantly different. We could actually add a Cohen's G for each of these. See the single binary variable with stikpet for calculating Cohen's G, but we can put this in a loop and it simply subtracts all the information it needs for Cohen's G every time. And then we can actually see how that is actually classified according to Cohen's G's rules of thumb. Alright, and that is how you can actually calculate or analyze a nominal variable using my library. As mentioned earlier, very quickly, there are alternatives. Alternative visualizations could be a Pareto chart where you actually see the cumulative percentages and the frequencies. You can do a pie chart, of course, and that's over here. And there's basic pie chart. There is a dot plot, which simply puts in a dot, and the dot size is then that each dot represents, in this case, 50 points. We can do a Cleveland dot plot, which is the same as a dot plot, but then only shows the top dot. We can do alternative measures. As mentioned earlier, there are quite a lot of different measures of qualitative variation, so I put in quite a few of them. This simply loops all over all the options I have in the function ME for measure qualitative variation. Oh, don't want that to change. And here you can see all of the results for them. It also shows the name of the measure and the source I've used for the calculation. Alternative tests, also quite a lot. We could perform a multinomial goodness of fit test. That takes a little bit longer, so I only select the first 20 because otherwise this will take way too long. It's an exact test, so that goes and takes a really long time for larger data sets. We can use a likelihood ratio test, also known as a G-test. We can use a freeman-tukey goodness of fit test. We can use a Niemann goodness of fit test, a modlog likelihood goodness of fit test, a freeman-tukey-read test, or even in the power divergence, if you don't specify anything, you just get the Cressy-Read version, but you can here actually specify a lambda, and then you can set that to any value you like. Alternative effect sizes, there's Cohen's W itself, of course. And as you can see, it's actually the same as we converted from the Kramer's V earlier. And of course, we can then still use that Cohen's W rule of thumb. There's also Johnston, Berry, Mika, and Mika E, which is a relatively newer one. And also this can be converted to cones W, and then we simply get again the same result there. So that's in a nutshell how you can analyze a nominal variable with my library. Hope this was helpful, and thank you for watching.